Two more chapters to go. Both of these chapters, 8 and 9, are on the chemical bond. There's so much information that the authors thought it best to split them into two chapters, which is a good idea. So we're gonna start with this chapter on just general concepts, and actually, it's a historical progression. Right, the earlier theories come along and then further develop, and then in chapter 9 we move into the modern age and what bonds are really like. But the information in this chapter is useful under many circumstances. It's like I mentioned at the very beginning. When you have a theory that fails, you have three options, remember? You can either modify it, you can restrict its use, or you can toss it out, start over. So the things that we're going to learn in this chapter are both modified and restricted use. Okay, let's get rolling here. First question is, what do we mean by a chemical bond? Very often we have an intuition about that. And it's simply whatever holds atoms together. That's about as simple as you can get. But the other question is, why do atoms even form bonds in the first place? I mean, aren't they happy by themselves? Well, the noble gases are. And we've gotten some indication as to why that's so, because the noble gases have completely filled orbitals. They don't need any more electrons. Whereas everybody else at some level does need some electrons, and they get that from their neighbors. And then not only that, but we want to know how the bonds form. If we can get an idea of both why they form and how they form, then we can make predictions and actually construct molecules from scratch, which is what organic chemists do for a living. Inorganic chemists do it too, but organic chemists are very prolific at creating new compounds. All right, we start with Dalton's atomic theory. Remember, he laid the foundations by defining or actually presenting a model of what the atom is at that stage in the early 19th century. However, even though it did lead us toward understanding, give us a basic understanding of chemical reactions, it didn't tell us anything, in fact, about the bond itself. It doesn't explain why atoms react. It just sort of sparked our attention, so to speak. All right. So we can think of a chemical bond as a force, right? A force of attraction. Whatever holds individual atoms together and binds them together in groups to provide another function. In other words, an atom has its identity. When it combines with other atoms, with this bond, it creates a new identity. I guess it's kind of like getting married, right? When you're single, you have your own identity. When you're married, you take on a new identity as a spouse. One thing we do know is that a bond will form. When a bond forms, the energy, let's see, when a bond forms, the energy of the compound is lower than the energy of atoms that form the compound. The universe, actually, this references thermodynamics. The universe is running down. In other words, the energy is becoming less and less and less useful. And the more stable situations are lower energies. So if you have atoms or molecules at this high energy level, they will trend toward a lower energy level. Now, it doesn't say how fast they'll get there, but that's a generalization that we can make about the formation of the bond. The bond lowers the energy of the aggregate as opposed to the energy of the individual atoms. All right. So we're going to start with a discussion of the ionic bond. It's the easiest to understand because it's purely electrostatic. In other words, a negative charged atom attracts a positively charged atom. And we have a fairly good understanding of how that works. This example, sodium chloride, has the center of the atoms, the nuclei, are 0.276 nanometers apart. That's really close, right? But it's not one nucleus against another. We can calculate the energy of that interaction using Coulomb's law. And if you haven't had physics or physical science, then Coulomb's law doesn't mean anything to you. Is that something you've had before? No, okay, you don't recognize Coulomb's law. Okay, that's fine. Well, here it is. The energy of attraction between two oppositely charged, well, actually, you can calculate the energy of repulsion if the charges are both the same, right? So it works for both, either attraction or repulsion. You have this constant, Coulomb's constant, right here. And then you need to know the charge on one of the species and the charge on the other species. Right? In the case of sodium and chlorine, it'll be a +1 and a -1. You multiply those together and divide by the radius or the distance between the centers of the charges. So in this case, it'll be 0.276 nanometers. And since the equation is given in terms of 2.31 times 10 to the -19 joule nanometers, then when you get these charges and the distance between them, the distance can be nanometers because the constant has units of nanometers in it and they will cancel. And these charges are dimensionless numbers. Right? It's either +1, +2, +3, +4, or -1, -2, -3. No, I take that back. Excuse me. This is a modified Coulomb's equation. I've seen it other ways. And it's modified for our atomic bonding. That way you can put a -1 and a +1 in here, and the units don't have to cancel because these don't have units. But this does have a unit that cancels and gives us the energy. Okay. Now, there are other forms of Coulomb's equations that are used for macroscopic situations where you have large amounts of positive charge here and a large amount of negative charge here, and how will they attract? And those values will be in values of coulombs, which is a unit of measure for charge. But this equation has been modified for our purposes, right, for atomic attractions or repulsions. All right, so if we plug those values in, we find that the force of attraction, which would be a negative value because in order to attract, one has to be positive and the other negative. That gives the overall negative value. So the force of attraction, actually the energy of attraction, is negative 8.37 times 10 minus 19 joules. Right? So it's very weak for individuals. but it's strong enough to draw them together. All right. All right. That's for an ionic bond where you have complete separation of charges between the two atoms. What if the atoms are exactly alike, right? You can't have opposite charge. Well, we typically don't have opposite charges of, say, a hydrogen negative ion here and the hydrogen positive ion here attracting. It just doesn't happen, simply because when they approach one another, they have the same electronegativities. They draw electrons with the same strength, so there's no incentive to separate the charge. So we need another mechanism, and that's the covalent bond, where they actually share electrons. All right, so what we find is when these two, that picture on the right shows you those red dots are what we consider the electron cloud. Right? Those are not, hydrogen doesn't have that many electrons. Those are positions that the electrons could occupy. It's a probability situation. So if you have a hydrogen here and we have all these dots around it, most of them are going to be right here. And then they kind of thin out as you get farther away. Okay. So it's a probability. They're more likely to be right here. When these two hydrogens approach one another, the electron probability density localizes between the two atoms. Right, so we see at the bottom, at the ideal distance between the nuclei, you have an increased density of electrons here. You still have probabilities out here, but most of the density is between the atoms. Right? They're actually sharing the two electrons that they bring to the dance. Right? One has one electron, one has the other. So that's what we predict as the electron density for a bonded pair of hydrogen atoms. What we're trying to balance here is that proton and that proton, and the electron that's assigned to each one. These will repel and the protons will repel. But this proton will also be attracted to that electron, and this proton will attract to that electron. So we're looking for a balance. How close can we get before the proton repulsion and the electron repulsion effects start pushing the hydrogens apart? And they meet at a certain distance, which is an ideal situation for the lowest possible energy. All right. And this is what this diagram is attempting to show us. The best way to interpret this graph is to read it from right to left. We normally go straight to the origin with our eyeballs. You know, we go down here and we say, all right, what happens from there? Well, we go this way and we go that way. But when we're trying to understand how this covalent bond forms and relative to its energy, it's best to go from right to left, because right over here is where the two atoms are separate. And together they have this much potential energy. And we've normalized it so that their potential energy separated is zero. So as they approach one another, you notice that the potential energy drops. That's good, because remember, lower energy means more stable situation. They always tend toward the lowest possible energy. All right. So as they get closer and closer, we've got this balance that's trying to form between the repulsions of the like particles, like subatomic particles, and the attraction between the unlike subatomic particles. And we reach that point at 0.074 nanometers distance between the two nuclei. Right? If we try to push them together closer, notice what happens. The amount of energy required skyrockets. Right? If you try to push them closer together, then they resist. Now that's what happens in the center of a star. if you get them close enough, then a new set of forces take over. And now you've got nuclear reaction. It's not chemistry anymore. Okay, so we're not going to go there. It just illustrates the fact that it's difficult to cause two hydrogen atoms to fuse without very high temperature and very high pressures. That's why it only occurs in nature in the center of a star. But the chemical bond forms easily. Right? It's trending toward this low energy state where the two hydrogens are sharing those two electrons, and the balance between the charge forces is optimal. It's minimal at this point. Okay. All right. So we've covered the ionic bond, where you have electrons are transferred from one atom to the other, and you get the electrostatic attraction. We can calculate the energy of that attraction using Coulomb's law. That's easy. And you have the covalent bond, where electrons are shared by the nuclei. And these happen between like atoms or atoms that have very similar electronegativities. All right, so you have the covalent bonds formed between elements on the right-hand side of the chart, the nonmetals. And the ionic bond forms between metal and a nonmetal. Now, there's another bond that we're not discussing here yet. That comes in the second semester, the metallic bond, where you get metals, how they interact with one another. So we're not going to go there. All right. So it's important to realize that in any bond, any chemical bond, the bond itself carries with it both ionic and covalent character. Right? If the atoms are exactly alike, two hydrogens, then we're pretty safe in saying that the covalent character is almost zero. It may not be exactly zero. Excuse me, the ionic character. Did I say that? I said covalent first, didn't I? The ionic character between hydrogen and hydrogen will be minimal, very, very small. But it's still there. And then when you bond sodium and chlorine together and you get an ionic bond, they still have some covalent character. They're sharing the electrons at some level. And this is all probability. Right? It's not something that we can directly observe. But it's important to understand that because they have both the ionic and the covalent character, that there are intermediates between the extreme ionic and the extreme covalent. And in between, the bond will have some measure of both. You want to call me? I got it silenced, so it just buzzes. Okay, so we're going to subdivide our characteristic bonds. We've got the ionic bond here. We've got the covalent bond here. We can subdivide the covalent bond into those that are polar and those that are nonpolar. The nonpolar covalent bond is, we have that word in quotes, equal sharing of electrons between atoms in a molecule. Doesn't have to be exactly equal. It just has to be very minimal. So that the molecule or the bond itself between this atom and that atom, it has a balance, does not have, say, positive here, negative there, a slight positive or a slight negative. Now, it may have a little bit of that, but it's below a certain level, and we take a practical approach. And we generally say that there's no charge separation, which is that little delta sign that I drew. The polar covalent bond, however, will definitely have a distribution of electric charge so that you get an uneven distribution. So if we were to draw that probability of electron density distribution, we'd have some in here, but we'd have most of the rest of the density around that one and just a little bit around this one. It'd be the negative charges would be shared unequally. Okay. In many cases, we can measure what that separation of charge is. In this case, we've got hydrogen and fluorine forming a compound, hydrogen fluoride. And when we do that as a gas, right, as a gas, we know if we put that in water, what do we have? Hydrofluoric acid, right? But as a gas, these are individual molecules, and this is a covalent bond. But fluorine has a much stronger, has a higher electronegativity than hydrogen. So it's going to be slightly negative, hydrogen is going to be slightly positive. There's a separation of charge. And we can measure that. All we have to do is put it between two calibrated plates with electric charge, and the alignment of the molecules in that between those two plates can be measured. And it can be measured how strong the charge separation is. All right, so we know it's real. All right, this is running over this again, the chemical bond, the force that holds atoms together. Why do atoms bond with each other? Well, atoms will bond with each other to form molecules if the energy of the aggregate is lower than the energy of the separate atoms. Right? We know that much at this point. How do atoms bond with each other? They either transfer electrons or they share electrons. One or the other. And like I said, in between. Okay. I've been using that term, I think, electronegativity, and we need to define it. It was introduced to us by a Swedish chemist, Berzelius, in 1811. It was studied by other chemists, right? Without using the term electronegativity. But Berzelius is given credit for fixing the definition and the type of properties that electronegativity described. And it was the impetus, that's too big a word. The motivation, how about that? The motivation for developing this concept was that there was an understanding that the bonds were not all alike. Some were like completely nonpolar, like hydrogen-hydrogen. Some of them, like HF, showed this polar characteristic. And there was a need to understand why that was. So over the years, and with the input of a number of different researchers, they came up with this concept of electronegativity. And basically what it says is that atoms have different strengths of attraction of electrons to themselves. And this is measured. Actually, it's not the atom sitting out here by itself and saying, how strong does it attract electrons? We want to use electronegativity in the chemical bond to help understand how it forms and what type of bond we get. So electronegativity is based upon the sharing of electrons in a chemical bond. So the measurements that are used to define electronegativity are based upon bonded atoms. Right? Linus Pauling came up with the first quantitative scale in 1932, and it's still the most popular one. In fact, we've got periodic tables that are set up with values, electronegativity values, that are derived from Pauling's equations. All right. Now, just as a side, Pauling received the Nobel Prize in chemistry in 1954. And he received it for, as I understand it, a single publication. He took all the information up to that point. It wasn't in 1954, but it was around in the 30s, because Nobel Prizes usually come a decade or more late. But he published a book called The Nature of the Chemical Bond. And what he did was he took all the information that he could gather from research that had been done over the years and tried to synthesize it into a coherent concept of the chemical bond. And the Nobel Committee thought it was worth a prize. It was that good. All right. He also got an independent Nobel Prize in 1962 for his anti-nuclear stance and his work for non-proliferation of nuclear weapons. Okay, so you don't have to remember how to use that equation. This is just for illustration purposes only. But this is how the Pauling's scale was set up. What he wanted to, the equation was set up in terms of energy, bond energies. So if we can calculate the bond energy of, say, that one between two hydrogen atoms, and we can calculate the bond energy between two other atoms, that, then there is the expected energy would be the bond energy of this one plus the bond energy of that one. I should put an energy here. The energy of that bond plus the energy of that bond divided by 2. Right. That's the expected bond energy that you would get from HX. Okay. And these are in relative terms. And notice in the brackets, this formula, of course, is very simplified. Right? It's much more complex than that to actually do the calculations. Okay. So this is the expected. You've seen that before in percent error calculations. This is the expected bond energy. We can measure the bond energy. Say if X were fluorine, FF, right? Then we'd have this HF, and we could measure that bond energy with equipment in the gas phase. Has to be in the gas phase because we don't want influences of phase changes, right? Liquid to solid, solid to gas, those things. We want it to be in the gas phase. So we're studying the bond only. And then you can measure this bond energy and get a value for that. Then you compare them, right? That little delta means difference, right? Anytime you see a delta, you got to subtract something from something else. It's a difference. So if we take the actual or the measured, they call it actual, I call it measured, minus the expected, then the difference between those two is a measure of electronegativity. If delta is 0, then there's no difference between the two, right? But we don't have any of those in the periodic table. They're all positive values. They may be very small values, but they're all there. They're all real numbers. Okay. So when Pauling got these numbers, he prorated them. He put them on a scale where they would be relative to one another, the type of scale that we could actually use. And they go from 0.7 to 4. All right. Now, how do they fit into the periodic table? Well, in the periodic table, right, we just kind of do like that, like that, like that. And then we have hydrogen here, and we have helium here. And in general, we know that fluorine has the highest value, 4.0. And the lowest value over here is cesium, I think. Cesium, it's 0.7. The trend is for lower left to upper right. Like ionization energy. Took me a second. Ionization energy is the same way, like we studied in the last chapters. 0.7 to 4, like that. So from left to right, you will increase, and from bottom to top, you will increase in electronegativities. Okay, so here's an artist rendition. Notice that as long as we stay with the representative elements on the left-hand side and far right-hand side, then the trend is fairly uniform from lower left to upper right. Once we get into the transition metals, they kind of roller coaster. Right? So things are not as reliable in there. If you want to use those values for any purposes, if you want to make any assumptions or predictions about the polarity of a bond, then in the transition metals, if you've got the transition metals involved, what you need to do is actually look up the numbers. Okay. So let's see if we can do some predictions. Let me see how much time I've got. About a half hour. And we're on slide number. I'm going to have to move it along. I've got a break positioned in the middle here so that we can pick it up again on Thursday, because I don't want to eat up your lab time. All right, so if we have lithium and fluorine react, which has more attraction for an electron? So the higher the electron negativity, the stronger the attraction for the electron in a bond. Right? Well, lithium's on the far left, right? Fluorine's on the far right. So the more attraction should go toward the fluorine. Okay? Right? How about fluorine and iodine? Well, fluorine is at the top of the halogens. Iodine is several steps down. So again, the attraction should be toward fluorine. Okay. We already did that. Lower left to upper right. Oh, explanation for why. Okay, here's why we think that across a period from left to right, the increasing electronegativity is due primarily to increasing numbers of protons. Right? You still got electrons in the same principal quantum number, right? At the same level. So they're about in here, but as we go from left to right, you may be adding electrons, but their distance from the nucleus is not much greater. There's not much difference. And you're adding extra protons. So when you add those extra protons, the electrons that you add don't shield those protons. So that gives them a little extra positive kick. We call it effective nuclear charge increases from left to right. All right. How about in a group? Well, as we go down in a group, we're definitely adding more protons. but we're also adding a lot more electrons that are at core and wrap another core. You're shielding those protons that you're adding in the nucleus. So the effective nuclear charge is actually going down as you go down in a group. Okay, does that make sense? Right, on the surface, it makes sense. Okay. So here's one practical way to use electronegativities to determine whether the bonds are polar, nonpolar, or covalent, polar covalent, nonpolar covalent, or ionic. And we look at the differences between the electronegativities. And now we're talking just about a bond. It can be a big molecule, but we're focused on individual bond between two atoms. And as the difference between, the delta between the two electronegativities increases, we increase the ionic character and decrease the covalent character. So as a practical matter, if that electronegativity difference between the two atoms is 0.2 or less, then we say the bond is nonpolar covalent. If it's between 0.3 and 1.4, then we say it's polar covalent. Unless, and I didn't put this here, unless that's between two nonmetals. Right? If you got a non and a non, then between 0.3 to 1.4, you have polar covalent. Right? But if you have a metal and a non-metal, and you have that difference, there's a break in here, and I think, let me see, do I have it on the next page? No, I don't. Okay. There's a break in here where we consider it ionic rather than polar covalent. And I think it's at 1.2, 1.4. Right? If you get up to 1.2, well, actually, if it's a metal and a non-metal, it should be ionic anyway, regardless of that. Okay, so that chart is talking about covalent bonds. The ionic bonds will be 1.5 or greater. And you're only going to get those with a metal and a non-metal. But there's also a range in there. And since I don't have it on the slide, I'm not going to hold you to it unless it shows up on your review document. If there's a question like that on the review document, then we'll cover that in class when we do the review. So let's see if we can arrange the following bonds from most to least polar. Right? The top one should be easy because it's different elements with fluorine, all of them with fluorine. So the furthest apart, nitrogen, oxygen, carbon, they're all on the same period, carbon, nitrogen, oxygen, fluorine. So this one is going to be the most polar. Right? So if we're going from most to least, this will be the most polar. It'll be greater than the next polar and greater than the next. Okay. Here we go. All right. The next one is a little more difficult because it's got a mix. It has a mix of bonds, mix of elements. Carbon and fluorine, which is pretty far apart. About nitrogen and oxygen, and silicon and fluorine. So now we've dropped down into another period. All right, which one's the furthest apart? Fluorine, silicon and fluorine are farther apart than carbon and fluorine. Right? So the strongest one here should be this one, and the next one should be carbon and fluorine, and nitrogen and oxygen are next door neighbors. So they're going to be very close to each other. They're going to be the least polar. All right. How'd that happen? There we go. I hit it by accident. All right. The last one, we've got a chlorine and a chlorine, right? That has to be the least polar. In fact, it is non-polar. Right? We ought to just throw it out because it's not even polar. It's covalent, but it's not polar in any significant amount. And then boron and chlorine and sulfur and chlorine. So boron and chlorine, boron is very far away from chlorine. Sulfur is right next door to chlorine. So sulfur and chlorine would be next, and then the greatest would be boron and chlorine. Right, and these are trends. We pick these up from the trends, not from the absolute values. We could verify these if we had the electronegativities and just do the math. Okay. So which of the following bonds would be the least polar yet still be considered polar covalent? Well, of course, oxygen is not considered polar, right? So we throw it out. Magnesium and oxygen is a metal and a non-metal. We throw it out because it's ionic. So we really only have to consider carbon oxygen, silicon oxygen, nitrogen oxygen. Nitrogen oxygen is the closest, they're the closest to one another. They would be the least polar, yet still be considered polar covalent. And if we look at the numbers, right, nitrogen minus oxygen, 3 minus 3.5. Right? So it's not less than 0.2. It's between 0.2 and 1.5. Right? The most polar without being considered ionic. Right? So that one, we need the furthest apart. And I believe silicon is further from oxygen than any of them. And its difference would be 1.7. Oops. Most polar without being considered ion. Oh, my mistake. Silicon and oxygen are so far apart. The difference is 1.7, right? That was greater than our 1.5, which makes it ionic. So we have to go to carbon and oxygen. That's the next possibility. All right, when we talk about these polar bonds, polar covalent bonds, we've got this concept called dipole moment. Dipole is fairly easy to understand, like it's two poles, right? A negative pole and a positive pole. The moment is drawn from physics. And to make a long story short, we represent it with an arrow. In physics, we say the moment of this object in either static or in motion is in that direction. Right? It's a vector sign. Whenever you see moment, it's a vector. In other words, you can have the same force or the same energy going in a direction, but it might be going that way or it might go this way, and they're not the same. And the reason we want direction is because when we start looking at the polarity of molecules, we have to combine the dipoles of all the bonds to say what effect does it have on the whole molecule. Right? We need to know what direction it is and what strength it is. So what we use in a bond, say we have hydrogen and fluorine again, right? We know that this one's going to be slightly negative, this one's slightly positive. The moment that we use is like that with a plus on this end. That shows you which end is the positive end, and this is which you're pointing toward the negative. That's called the dipole moment right there. All right. There it is. Example. Two factors determine the dipole moment of any molecule. Now, when we talk about molecules, in this case, the dipole moment of the bond is the dipole moment of the molecule because there's only one bond. But if you have something like water, right? Water is shaped like this, right? And it has a dipole moment here, and it has a dipole moment here. Because oxygen has a larger electronegativity than hydrogen. So it's facing this way, this way. When we combine them in what we call vector summation, you ever heard of that term? Adding vectors together. We get a summation here like that. Okay. So that means this side of the molecule is the negative side, and this side of the molecule is the positive side. Vector summation is something we use in physics. If we have a point here and you got a force pulling on it this way, and you got a force pulling on it this way, then you sum what's the net force and direction in this case. Well, in this case, we do a parallelogram like this, same length as that one, and then one same length as this one, and then our vector summation is right here like that. Okay, so that's what we've done here, only without drawing the parallelogram. So in order to determine the polarity of the molecule, we need to have polar bonds. Okay. If you don't have polar bonds, then the molecule is nonpolar, period. Now, where would you have an example like that? Well, let's see. How about phosphorus? Right, phosphorus occurs like that, or sulfur. Sulfur occurs like that. Right? They're all bonded, same atoms bonded together here, same atoms bonded together here. You got no polar bonds. Neither one of these can be polar because the bonds are not polar. But if you do have polar bonds, then you need to know symmetry. What's the geometry of the molecule? And in this case, the geometry is such that these add together in that direction. If water were shaped like this, right, then you would have like that, and they would cancel each other out. And even though you have polar bonds, you have a nonpolar molecule. Okay, so you need those two factors. You need to know the polarity of the bonds, and you need to know the geometry. We're going to get to the geometry eventually. All right. All right, so there's my example of water. Now, we still have, this is the overall polarity of the molecule, but we still have the bonds individually polar. That means that each of those hydrogen atoms is going to have its slight positive charge, and the oxygen is going to have its slight negative charge. And that's why when water has such a high boiling point, right? Water, if we follow the homologous series of the dihydrides of oxygen, sulfur, selenium, tellurium, we find that water should have a boiling point of like -30 or something like that. Right? But it has this polarity, which gives it intermolecular attractions, right? The negative side of one molecule attracts to the positive side of the other, and that energy, that lowered energy, has to be overcome to get them apart and make them boil, change phase. So actually, it's fortunate that water is that way. Otherwise, we'd be in big trouble. Okay, here's an example of a molecule that has polar bonds, carbon dioxide. In fact, it's not drawn correctly. It should be like that. Not a single bond, but a double bond. And the dipole moment here is toward the oxygen. But they're equal and opposite. So they cancel one another out. We have polar bonds, but we have a nonpolar molecule overall. All right. Now, I want to get into this eventually, but I don't want to get too far ahead of ourselves so that we lose all meaning. These are just examples. Right? We're gonna get to the point where we can predict these shapes later. But these three examples, carbon dioxide we've already looked at is a linear molecule, right? With equal but opposite dipole moments, right? They cancel each other out. If we have a planar molecule where we have an atom in the center, let's see if I can think of an example. We have an atom in the center and we have, that's not a good example. Let's do this. Let's make it even more different like that. Yeah, there we go. So each one of these has a dipole moment this way. Right? And this equilateral triangle says that all of those are pulling with the same force in symmetrical directions, so they cancel one another out. Oh, they gave us an example there. Sulfur trioxide. And then the last example is a tetrahedron, where you have four atoms bound to a central atom, carbon tetrachloride. And the polarity of the bonds, the carbon-chlorine bonds, cancel one another out because it's a regular shape with equal dipole moments pulling in just the right position so that they cancel one another out. Those are all nonpolar molecules with polar bonds. Okay. So we have stable compounds when the atoms in the compound acquire the electronic configuration of a noble gas. All right. So if we look at it that way for water, let's use water. Say we have oxygen. We've done Lewis dot structures, haven't we? We haven't done Lewis dot structures. Okay. Well, how many electrons does oxygen have? It has 8. Right? It has a 1s2, a 2s2, and a 2p2. No, 2p. 4. That's 4. That's 8. So, how many more electrons does it take to make it look like a noble gas? Right? Well, we look where oxygen is. 2 steps to the right is neon. We just need 2 more electrons, right? 2 more electrons would look like neon. 1s2, 2s2, 2p6. Where is it going to get those electrons? Well, if it bonds with a metal, it's going to take the electrons and keep them. Okay. But if it bonds with a non-metal, it has to think it has the, in quotes, it has to think it has the configuration of a noble gas simply by sharing with something else. So hydrogen has 1 electron. This hydrogen has 1 electron. This oxygen, I'm going to go ahead and use the dot structure, has how many in its valence shell? In its outermost shell, right? 6, right? It has 6 electrons. Well, for mutual benefit, if they share 2 electrons to form 1 bond here and 1 bond there, then hydrogen thinks it has 2 electrons, right? So it looks like helium. Correct? Helium has 2 protons, 2 electrons. And the same thing on this side. It looks like helium. Well, oxygen now thinks it has 10 electrons. It looks like neon. That's one way of explaining why atoms bond. Now, with period 2 and period 3, right, those that start with lithium and go to neon, or sodium and go to argon, the outermost shell, the 2s and the 3s, right, 3s2, 3p6 would be the next one, the next row down, the next period. What we're looking at is a complete valence shell has 8 electrons. That's the octet. Okay. So now oxygen has its octet, 2, 4, 6, 8. That's where that concept comes from. If you've seen it in some other courses, like biology courses, or maybe even in A&P, then that's where the octet comes from. Once you get down into the 4th and below, the 4th period and below, now you have access to d orbitals. And the octet doesn't work as well. Sometimes it does, sometimes it doesn't. So 10 forms a 2+ ion or a 4+ ion. Well, why is that? Well, let's see. 10 is in the 4th period, and over here it has what? It has 4s2 and 4p2 as its valence. So 10, 50 can be written. We've done electronic configurations. I know we have. Yeah. 10 can be written like this. It has the core structure of krypton, right? But it also has 3d10. But the valence is the highest principal quantum number. So if it gives up these two, it takes on a +2 charge. But if it gives up those two and these two, it takes on a +4 charge. That explains why the most common ions of 10 are 2+ and 4+. We can say the same thing about lead, right? Lead's in the same group, right? Only it has, instead of 4s and 4p, it has 5s and 5p. Lose 2, 2+, lose 4, 4+. Bismuth is over 1, I think. Where is it? Here it is. Right next. So it has a 2+. It has 5 S2 and 5P3. So in this case, it prefers to lose those 3, makes a 3+. Lose these 2 in addition, makes it a 5+. That explains its charge, its preferred charges. And thallium is over here. It only has, let's see, a 6. Did I say 5? 1, 2, 3, 4, 5, 6. That would be 6. I'm sorry, 6. And actually, this would be 5 and 4. But thallium only has 1 p electron. It has 2 s electrons. So if it loses that 1 p, it's a plus. If it loses the other 2 s's, it's a 3+. So this is just explaining how these charges are preferred for these different elements. Because by losing those 2, or 4, or 1, or 3, if they lose all the p electrons, then they're back at a noble gas configuration. Let's see. Oops. There we go. So when 2 nonmetals react to form a covalent bond, they share electrons. And in a way, such a way that completes their valence electron configuration, makes them look like noble gases. When a nonmetal and a metal react to form a binary ionic compound, then they actually do form the noble gas configuration in their electronic shells by transferring electrons. Okay. So the concept is similar, but the physics of the process or the chemistry of the process is a little different. Because in covalent bonds, you're just sharing the electrons and you kind of think that you look like a noble gas. But in ionic compounds, you actually do transfer electrons, and that gives you the electronic configuration of a noble gas. The isoelectronic series is based upon that concept. These neutral atoms or ions, if they have exactly the same electronic configuration, then they're considered isoelectronic. Iso means same electronic configuration in a series. Now, in this particular one, we're focused on the neon. Neon has 10 electrons. So if we add 1 to fluorine, it looks like neon. If we add 2 to oxygen, it looks like neon. If we subtract 1 from sodium, it looks like neon. Subtract 2 from magnesium or 3 from aluminum, and they look like neon. Right? Those all have exactly the same electronic configuration. But one thing we didn't change was the number of protons. Right? What happens if you change the number of protons? You get a different element. Right? We can't mess with the protons. All right. I'm running too far behind. I'm going to just show these: alkali metal, alkaline earth, noble gas, and halogen that are isoelectronic series. And in order to do that, we've got to make ions out of all of them except for the noble gas. And this is the electronic configuration of each one of those. It's exactly the same. The number of electrons are going to be the same, but the number of protons are going to be different. All right? Because that defines the element. So we can predict many properties, and several of them we've done already. The atomic size, the ionization energy, the electron affinity we've done in previous chapter. We didn't do ionic radius. They're a little trickier to do. We had reference to ionic radius in a couple of our review problems, but we didn't spend a lot of time on it because it's really a difficult subject. And to understand it, you have to deal with reality. You have to actually make the measurements. Electronegativity, we've talked about that one. Electron configurations. We can predict the formulas of ionic compounds because we know that their charges, or if they're type 2 compounds, we're given the charge. Right? For these that have multiple possible charges, right, you have to be given the charge in order to write the compound. And we've learned how to rank bond polarities. So the factors that influence the stability and the structure of solid binary ionic compounds, well, one way that's developed to define how strong the bonds are is called the lattice energy. So, the lattice energy is based upon forming the solid ionic compound. I'm going to use a real example. Say we form sodium chloride solid. In order to write this in terms of lattice energy, how much energy did it give up when it went from this to that? It's an exothermic process every time. We go from sodium positive ion as a gas and chloride negative ion as a gas. And that forms the solid. Go from these two gas ions to that solid. That's the lattice energy. Okay. And that's what in English, That's what I just wrote on the board. Now the energy, yeah, it wants to stay open. The lattice energy can be quantified. And notice there's a similarity here between this and the Coulomb's equation that we watched earlier, except the K is different. Right? It's based upon the difference in charges and the distance between the two, right? When they form the solid, and we need a proportionality constant, and that constant varies with the compound that's being formed. All right, so if we look at how an ionic solid is formed, okay, I'm going to give it a few more minutes to see if anybody else shows up, and I'll just keep talking. Hopefully, to get to my, I'm not going to make it. No, I've got too many more slides. So as soon as we've got enough people to form our groups, then we'll break. So in order to form an ionic solid from the metal and non-metal elements, we have to work from the most stable form of the metal, which is usually a solid, right? Right. There's only one metal that's not a solid at room temperature, right? Mercury. So we generally work from a solid, and the non-metal is very often a diatomic gas. So this is our example. These are our starting materials. So in order to get them to the solid, we're going to go through several steps. First thing we have to do is change this to a gas. Right? So there's sublimation, right? Sublimation changes a solid to a gas. And what type of process is this? It's endothermic. We have to put energy in. Right? Energy goes in. It's endothermic. All right. Then what do we have to do? Well, then we have to form the ion from this one. Right? So we take the gas and we add energy, endothermic, and we form the ion of that gas. Right? That's the ionization energy. Ionization energy. Okay. Now we've got this gaseous metal ion. Now we're going to go to the non-metal. We've got to dissociate these two from one another. Right? So what we need is only 1 mole of this. Right? So we're going to use half a mole of that to that. And this is the, what do they call it? Dissociation. Energy. And this is endothermic. Okay. So far, we put energy in and got nothing back. So then we have to ionize this one. Right? So remember, I think it was the last chapter. This is electron affinity. Right? Electron affinity. And this is going to be an exothermic process because an electron that's at infinity and comes to be bound to the atom is at a lower energy state. So it has to give up energy to get there. Right? So this is exothermic. We're starting to get some energy back. All right. Now we've got this ion as a gas and this ion as a gas. We can put them together. And that forms the solid. And that's our well, they didn't name it there. Right? It was just like the previous. There we go. Just like that one. That's the lattice energy. This is lattice energy. And this is exothermic. In fact, it's extremely exothermic. Right? If you could isolate this particular process, and some chemists have done that, then you get a huge amount of energy back. Right? And here's it's kind of small print, but if these are the steps down here, let's see, if we go from, electron affinity, we have to put in, we get energy back for this one. The blues are energy back and the yellows are energy in. So we put energy in to ionize the metal. And we've, okay. This particular chart is using Hess's law. Remember Hess, where we combined equations to get our outcome equation? So what they're doing is they're taking these reactions and combining them all together to get the preferred reaction. So this diagram, and I just noticed that, this diagram doesn't show these steps individually. It shows bona fide reactions that are brought together to produce this reaction, where we have metal solid plus 1/2 X gas yields in X solid. This is the overall reaction. And that slide shows you component reactions that are used to determine the energy for this one. So I need to replace that slide.
Desiree said she'd be here in about 15 minutes.
Who's that?
Desiree.
Okay. Well, we've got time. If we have to break this lab in half, we can do that. As it's in 2 steps, and you know that because you've already read the method and you prepared your notebooks and you know all the details.
Now, on the last one you did.
All right. So here's an example. If we follow this pattern where we sublime lithium, right, and then we ionize the lithium atoms, and there's the energies associated with each one, and we see the signs. And then we go to, let's see, then we go to the fluorine and dissociate the fluorine, and then we add an electron to the fluorine in the next step. And then we get the lattice energy value, and we can add all those together. Right? And when we go up, we're adding energy. Right? That's endothermic, and we come down, that's exothermic. So the biggest exothermic in this whole thing is right here. This one right here between lithium ion, fluorine ion, both gas make the lithium solid. That's the lattice energy. That's the biggest jump of all, and it's exothermic. So if we just go with this equation, then the value should be 617 kilojoules per mole for the reaction. Well, not that reaction, but this reaction. And if we go through each one of those steps and add them all together, we get the same value. Overall change is exactly the same. So Hess's law works with this one, whether it's those individual reactions or it's these hypotheticals. Okay. All right. So I mentioned earlier that there's a continuum between covalent and ionic. Right? Every bond has ionic character and covalent character. Some of them are really, really close to ionic, but they're not 100%. Right? No bonds ever reach 100% ionic character. Even with those compounds that say are between fluorine and cesium, right, the farthest from each other, there's still some covalent character. Now, we can quantify those values. Let's see. You may need me to leave this up here. Okay. We can quantify the ionic versus covalent character. If we calculate the dipole moment for two positive negative ions, and then we measure the dipole moment, like we did in that example with hydrogen fluoride between those two plates, the negative and positive plates, you can measure the dipole moment there. You measure that, and then you can calculate it based upon their electronegativities, and then ratio those two. The measured versus the calculated times 100 gives you the percent ionic character. Okay. And when we do that, we find these examples of compounds, and the percent ionic character should be relatively high for metal, non-metal compounds that are particularly far apart on the periodic table. The ones that are closer together are going to have less of an ionic character. And those are down in the lower left-hand corner. And we see that the percent ionic character does follow a trend with the electronegativity difference between the two. So the higher the electronegativity difference, the higher the percent ionic character. That's really basically all that shows you. What we're saying is that with this color scheme, right, the red ones have greater than 50% ionic character, and the blue ones are less than 50% ionic character. Right, so they're starting to favor covalent versus the red ones that are favoring ionic character. So what we end up doing is we have an operational definition for ionic compounds. And if the ionic compound conducts electricity, when it's either melted or if we can dissolve it in water, then if it conducts electricity, then we consider it an ionic compound. So we can definitely dissolve sodium chloride in water. And when you stick the ends of the two poles of a battery in there with a light in between, the light will go be bright. Right? We call those electrolytes. Okay. Now we're going to get to a little bit, a few more minutes. We're going to talk a little bit about models. Trying to understand the nature of a chemical bond. And this is a reminder, right? I've talked about models before. A model is some type of attempt to either explain in words, mathematical formulas, or sometimes even in a three-dimensional construct, the how nature operates on the microscopic level. Now, models are never perfect. In fact, does this go any further? Yeah. Fundamental properties of models. Here we go. The first rule is a model is not reality. A model is a tool to help us understand reality. Models are necessarily oversimplifications. And as a consequence, many models are wrong, right? But just because they're wrong doesn't mean they're not useful. I mean, we can find, what is it, Edison, a reporter asked Edison, how many times did he fail to make a light bulb? Or he said something like, I understand you failed 99 times to make a light bulb. He says, I didn't fail. I just found 99 times that it wouldn't work. You only had to find one time that it worked. So if the results of an experiment, for instance, don't come out the way you expect them, you can still learn something from them. Models tend to become more complicated and as they are modified with age. So that's one of those three possibilities, right? If your model, and models are always attached to a theory, right? If your theory fails, then you can either modify it, or you can restrict its use, or you can, let's see, what's a highbrow term for throw it out? Retire it. You can retire the model, retire the theory, right? If we modify it and continue to modify it, they tend to become more and more complex. In fact, that's usually the pattern. We don't want to retire or throw away a theory unless we've tried modifying and restricting to the point where neither works anymore. Usually modification. If you modify it ad nauseum, eventually you'll reach the point where you just have to throw it out, start over. And number 4, we have to understand the underlying assumptions in a model so that we don't misuse it. That's probably what's basically wrong with all the climate change models. None of them work. Because those who propose them and those that are adherents to man-caused global warming are going to use them to advance their agenda rather than use them the way they were designed, right? And they'll never admit that they're wrong. That's characteristic of a religion, which is global climate change. It's long past the point where it's science. It's no longer science, it's a religion. 5, when a model is wrong, we often learn much more than when it's right. I already mentioned that one. So, didn't I mention this earlier in the semester when we talked about theories? I'm sure I did. Right, here it is again. You can restrict the model's application. Newton's the best example there. Newton's laws of motion work under certain circumstances, right? When you get down really small or you get really big, like black holes, then Newton's laws just completely fall apart. They don't work anymore. So we restrict their application, right? Somewhere in the middle. If the masses get too big, now we have to go to relativity. And if they get really, really small, we go to quantum mechanics. And there are physicists that spent their entire lives trying to blend all those together into a single coherent theory. Nobody's made it yet. They're coming close, right? But they haven't made it quite yet. We can modify the model to accommodate the new conditions. So what is it about a model that we want to have? It's functional because it can be changed. And if we can change it, we can see how that change affects the outcome. That's where theories are up here and laws are down here, because laws are chiseled in stone. They only work, right? You put these numbers in, you always get those answers. That's it. We don't even know why. But theories are designed to be changed, to be modified so that you can get some basic understanding of what's underneath, what's happening at the microscopic level. Right? Or throw it out and start over. Like J.J. Thomson plum pudding model for the atom. Remember that one? Right. That was all it took was Rutherford's gold foil experiment, and J.J. Thomson's plum pudding model was dead. Okay. Let's see. We only have 2 groups so far, don't we? Yeah. What happened to everybody else? Anybody know? Are they sick? Nobody knows. Well, there's been stuff going around. I guess that's good an assumption as any. All right, let me see how much more I got to go, and do I need to stop? Oh, we might be able to do it. Since we can do the calibration part today, and the excellent and the 2 titrations. One is to standardize your base, sodium hydroxide, and the other is to use that standardized base to determine the molar mass of citric acid. I mean, it's better if we can do it in one day, because then you don't have to reset it up everything again, but we don't have to. I mean, we could finish it next week. Bond energies. What do we mean by bond energy? Well, it's the energy required to break a bond. Right? How much energy do you have to put in to make those 2 atoms separate? And it's always endothermic. Bond energy is endothermic because you're starting with a bonded pair, and you're putting energy in to break the bond. So it goes in. It's endothermic. When a bond forms, the bond energy releases energy, because it's trending toward a lower energy state, and it has to get that energy up. Right? So it depends on the sign. If it's a positive sign, we're talking about adding to the system, just like always. Right? It's all relative to the system. If the value is positive, it's endothermic. If the value is negative, it's exothermic. All right, we have 3 types of bonds that are most commonly seen. I think there are other kinds, but they're really weird. So we're just going to stick with these 3: single bond, double bond, triple bond. The single bond always represents 1 pair of electrons between the atoms, and we represent that with a single line. A double bond would be 2 pairs of atoms, and we have 2 lines for that one, and you probably see where this one's going. A triple bond has 3 pairs of electrons, and we represent that with 3 lines. Okay. Now the trend is, overall, the double bond brings the atoms closer together than the single bond does. So the bond length shortens with the double bond, and the triple bond shortens even further. Okay, and they're stronger. It takes more energy. You have to put more energy in to break a triple bond than you do a double bond, and more to break a double bond than a single bond. Now, as far as the distance goes and the energy you put in, it's not a linear progression. It doesn't take 3 times as much energy as a single, or this one 2 times as much energy as a single. It takes, it's not double, it's less than double, and this is less than triple the energy. And there are reasons for that, but we don't have the background to get into that right now. All right. Now, the bond energies have been compiled in this list. Single bonds between these 2 atoms are given as values in kilojoule per mole. Kilojoules per mole of bonds. All right. So these are all positive values. So what does that mean? That means these are written in terms of bond energies you're putting energy in to break the bond. But if they're 2 separate atoms and they come together, they're going to give up that amount of energy. Right? So it works both directions. It's just a different sign. Now, why do we need all these? Well, if we want to calculate the enthalpy of a reaction, all we need to know is how many of each type of bond there is in the reactants and in the products And we can calculate the enthalpy for that reaction from the bond energies. All right. We've already talked about this. I'm not going to stop there. All right. So here's the formula. The energy, the bonds that are broken would be the reactant side. Right. So if you want to know the enthalpy of a reaction, if you have X plus Y yields A plus B. Well, let's see, X, Y, and let's see, chose the wrong symbols. Let's say you have, let's use real. Let's say we got hydrogen gas plus oxygen gas yields water. Okay, so to balance that, I need 2 of these and 2 of these. That was crap. Let's try this one. Okay, so in order to make that calculation for the enthalpy of that reaction, you need to know how much energy does it take to break those bonds. Right? So you add those all together, sum them up. Right, and this is going to be the energy required to break those bonds. Let's see, did we give that a name? No, we didn't. This is, well, the way the chart's written, these are positive values. Right? So we keep those positive values. And these are break bonds. So how would we do that in a practical way? Well, what's the bond here? It's this one like that, and this one like that. Okay? But there are 2 of these. So we would do 2 times the hydrogen-hydrogen bond energy. And then we would add 1 times the oxygen double bond energy. Okay? That would be on this side. Then we would subtract the energy we get back. And we use the bond energies for that side. Right? And this negative turns it into exothermic. We get the energy back. Right? So you just keep the positives over here. In this case, we have 2. How many do we have here? Well, we have an oxygen, hydrogen. Right? And we got 2 of them for this one. But we have 2 of each. So it's 2 times 2 times that. So it's 4. It's 4 times, let's see, bonds formed. Let me be consistent here. Bonds formed. So down here, it'd be negative, and this would be 4 times the oxygen-hydrogen bond energy. Okay? And that's the way you would calculate the delta H for that reaction. So for this example, everybody got that one? That's okay. I figured an example would be easier to follow than the mathematical formula. If we want to do delta H for this reaction, right, now we know how to calculate the delta H for an unknown reaction if we have component reaction using Hess's law, right? But this way we do it with the bond energies. So that's another way of calculating the delta H for your reaction. In this case, they look the same, don't they? Right? We've got N like that one. But on this side, we have CH3. Now we have carbon on this side. So what's happened? Well, the way we write organic equations, this would be like writing that. Hydrogens would be up here. And then this would be bound to a nitrogen and then to the carbon. So on this side, we would have these 3 hydrogens. And instead of bound to the nitrogen, this would be bound to another carbon. And then the triple bond to the nitrogen. Okay, that's the only difference between those two. Notice that these are the same on both sides. The carbon hydrogen bonds are the same. 3 of those on this side, 3 of those on that side. So we don't even have to pay attention to those, right? Because the bond energy here is the same on that side. We're going to subtract it. So we just ignore that one. What has changed? Well, we've got this carbon nitrogen triple bond on both sides, right? We can ignore that one too, because it's the same on both sides. The one that's changed is this one, that carbon nitrogen single bond and the carbon carbon there. So we would take the value here, the energy for this one, and minus the energy for that one, and get our value. Right, so carbon nitrogen is 305. And then carbon carbon is 347. And subtract. So we're going to come out with a negative value, right? That would be 42. Negative 42 kilojoules. Okay. I mean, you can go ahead and do all that other stuff if you want, but it's not necessary. Takes extra time. Time is a premium on an exam. Okay, now we can pause.